We are going to introduce our work, Exploring Probabilistic Modeling Beyond Domain Generalization for Semantic Segmentation. Semantic segmentation aims to assign a class label to each pixel in an image, allowing machines to understand scene structures precisely. However, in real-world applications, models are often deployed in unseen domains, such as nighttime, fog, or unfamiliar urban scenes, where the visual distribution shifts significantly. To tackle this, domain generalized semantic segmentation is proposed to enhance the model's robustness in unseen environments without access to target domain data during training. To achieve robust segmentation, there are currently two approaches. The first approach is to enhance its training diversity by generating style-variant images through augmentation functions or generative models. However, the performance is still bottlenecked by the capacity of the segmentation backbone. Thus, the domain-invariant representation learning-based methods is proposed to remove domain-specific information via feature normalization, encouraging a more consistent feature distribution. Nevertheless, these methods often overlook the intrinsic structure or prior knowledge embedded in the source domain, resulting in suboptimal generalization. To bridge this gap, we introduce a probabilistic modeling framework that explicitly integrates latent domain prior to model domain shifts in the semantic segmentation task. By formulating latent domain prior within a variational inference framework, our method enables principled estimation of domain prior that serves as conditioning variables, thereby guiding segmentation models to generalize more effectively on unseen target domains. In practice, the latent domain prior is not directly accessible. To address this, we introduce a variational posterior to approximate the true posterior distribution of the domain prior. The estimation can be further formulated under the evidence lower bound, which defines as our training objective. Specifically, we will optimize two terms, maximizing the expected log likelihood conditioned on the latent prior and minimizing the KL divergence between the variational posterior and the estimated prior. To achieve this target, we propose the probabilistic diffusion alignment framework, which can be seamlessly integrated into any pre-trained segmentation model. By applying data augmentation to the source domain, PDAF simulates domain shifts and generates pseudo-target images that preserve semantic content while introducing appearance-level variation. Based on this, we introduce the Latent Prior Extractor as the variational posterior to learn the optimal latent domain prior from cross-domain relationships. On the other hand, to handle the absence of target distribution at inference, we introduce the Diffusion Prior Estimator to estimate the latent prior directly from target inputs. This module leverages the iterative denoising strategy of diffusion models to progressively approach the optimal latent domain prior. To support latent domain prior learning, we introduce a prior constraint loss that encourages consistency between the estimated and optimal priors. Additionally, we propose the domain compensation module, which integrates into the segmentation network and performs conditional feature alignment using the estimated latent domain prior. This allows the model to adaptively align features across domains during both training and inference. At inference time, only the lightweight diffusion prior estimator and domain compensation module are retained, reducing overhead while preserving generalization. To evaluate our method, we adopt a single-source domain generalization setting, where the model is trained on one source domain and tested on multiple unseen target domains. The experiments are conducted on 7 diverse datasets, which cover various cities, styles, and challenging conditions such as fog, night, and adverse weather. In addition, to demonstrate the generality of our approach, we apply it to both a CNN-based model, DeepLab 3+ with ResNet 50 backbone, and a transformer-based model, Mask2 Former, with SWIN transformer. And all comparisons are conducted under the same training protocol and evaluation setup as prior domain generalization methods. Our method consistently outperforms existing domain generalization approaches across all benchmark datasets, achieving state-of-the-art performance. Notably, PDAF improves both CNN-based models like DeepLab 3+ and transformer-based models such as Mask2 Former, demonstrating strong flexibility and compatibility. Moreover, under real-world adverse conditions in ACDC, our method achieves robust performance gains across all corruption types, indicating that the latent domain prior effectively compensates for degraded visual features. We further provide qualitative comparisons across unseen domains, where our method consistently produces more accurate and structure-preserving segmentation results. In particular, our method better captures boundaries and fine-grained semantics under challenging conditions. The ablation study shows that each proposed module contributes positively to generalization performance, with the latent prior extractor playing a key role in posterior regularization. In addition, both the semantic consistency and prior constraint losses significantly enhance feature alignment and domain prior estimation. We also observe that using a compact latent prior and a small number of diffusion steps provides the best trade-off between accuracy and efficiency. Thank you for your attention. Please read our paper to find out more.